Okay, we'll start off with electrochemistry today. What are basic things we need to learn from this topic? Let's see. Uh, we have two types of cells, right? Whenever we discuss about electrochemical cells, electrochemical cells, we always come across two types of cells. One is galvanic cell, which galvanic cell, which will convert chemical energy into electrical energy. Then we have electrolytic cell, which will convert electrical energy into chemical energy. While here the cathode is while cathode is positive, anode is negative. While electrolytic cell, cathode is negative and anode is positive. While this is spontaneous cell, this is a non-spontaneous reaction. Okay. Common thing about both of them is both will have a redox reaction. Both will undergo redox reaction. Got it? Now, when it comes to galvanic cell, in galvanic cell, we got it is also called as voltaic cell, and there will be two parts of it, correct? And these two parts are called as half cells. Left side and right side we will have. Left side we have anode, right side we have cathode, and both of them are connected by a salt bridge. And outside they are connected to voltmeter switch, and through wires they are connected to cathode. The first of the kind which was started was with zinc sulfate as the solution, and here copper sulfate as the solution. Left part is usually called as the anode cell, right part is called the cathode cell, or this is the anode half cell and cathode half cell. Oxidation happens always at anode. So at anode, oxidation will take place where, let's say, zinc is getting oxidized to Zn2 plus 2 electrons, while reduction takes place at cathode where copper 2 plus is accepting those electrons to convert into copper solid. Overall reaction is zinc plus Cu2 plus is Zn2 plus Cu. See, number of electrons given by the anode and number of electrons taken by the cathode should always be same. Okay. Next. How do we represent the cell? Typically, when you notice the cell, especially this Daniel cell is represented this way. Zinc is getting oxidized into the solution, right? Then a double line, which means a salt bridge, and then copper sulfate is getting converted into copper. Single line represents the phase difference. Single line represents phase difference. Double line represents salt bridge. When there is a phase change, we will add single line. And if you have to show anode and cathode separately, then we'll show a salt bridge in between. Okay. For example, if at all I show it this way, zinc is getting converted to Zn2 plus of C1 concentration molar. And then I have H plus aqueous of concentration or C2 concentration molar, which is converting into H2 gas, which is present at platinum. Correct? Another important thing is platinum here is inert electrode. Inert electron should always be at the extremes, either on this extreme or on this extreme. Okay, always on the extremes. So in this case, zinc is getting oxidized to Zn2 plus 2 electrons, while 2H plus 2 electrons is getting converting into H2 gas. So this is left part is the anode reaction. This is the cathode reaction. That's how it represent. Clear? Now, what is the relation between delta G and electrode potential? Electrode potential. See, first of all, electrode potential represents how much amount of electromotive force an electrode would have. Okay, electromotive force as in how much amount of what do you say voltage difference that it can maintain with the solution. Correct. And here we are converting a particular energy form into another energy. So we say that the EMF of cell is converted into useful useful electrical work. So if you are able to convert that into useful electrical work, we can say work done work done is equal to charge into potential. And charge in this case is N into F multiplied by E cell. So F represents Faraday. I'm sure all of you are aware of that, which is 1 more electron charge. N represents number of moles of electrons. And E cell, here this represents electromotive force of of the cell. If it is for an electrode, it will be of the electrode. So therefore, delta G, which is the useful work, can be represented as minus NF E cell. This minus is introduced to map up with the thermodynamic unit, because in thermodynamics, delta G always need to be negative for spontaneous change. Since all these terms are positive, to make sure that delta G is negative, we added this negative part. So which means if delta G is negative, then E, if E is positive, which means it is spontaneous. Okay. If delta G is positive, which means E must have been negative, and this is non-spontaneous. And if delta G is equal to 0, that means E must have been 0, and this is at equilibrium. The cell is at equilibrium. Okay. So I guess this part is clear. Next. Whenever we write a representation like this, zinc becoming Zn2 plus, okay, it means we are talking about an electrode, right, where zinc is converting into Zn2 plus, which means it is an oxidation. So if I write the same thing here as zinc to Zn2 plus, then we read this as oxidation electrode potential. Oxidation electrode potential. While if I write something like copper 2 plus to copper, and here also I need to, if at all I show it this way, that means we are talking about reduction electrode potential or electrode reduction potential. Okay. If anything which the not is being used, that means we are using it as standard conditions. Standard conditions. And standard condition is solution must be 1 molar concentration to start with, and partial pressure of gas must be 1 bar to start with. And temperature typically is always maintained at 25 degrees. Okay, these are the standard conditions. So all of you got an idea how to represent and what is the value. For example, if you notice, there is standard hydrogen electrode which will help us measure what are various electrode potentials for different cases. Okay. According to standard hydrogen electrode, the basic assumption is E naught of H plus to H2, that is reduction potential of hydrogen or oxidation potential of hydrogen. Here, oxidation potential of hydrogen is equal to 0. Right? That is the standard which we have maintained. And E naught value, using this, we will be able to figure out what will be the value for others. For example, E naught of zinc to Zn2 plus, which is oxidation potential, has found to be 0.76 volts, which means if I connect hydrogen electrode with a zinc electrode has the tendency to get oxidized. While if you notice Cu2 plus to Cu, this is found to be 0.34 volts, which means copper, if it is connected with standard hydrogen electrode, copper will get reduced, and hydrogen will get oxidized. Okay. So, which means the reactions which we will expect here is this one. Zinc plus H plus 2H plus is giving Zn2 plus H2. This is the reaction which we can expect here. Here, spontaneous reaction is zinc copper 2 plus H2 converts to 2H plus copper. Okay. Now, if at all I want to write every electrode potential only as a reduction potential, so then that is called standard reduction potential. Standard reduction potential. Okay. Standard reduction potential is extremely important to understand, which one will overpower the other elements or molecules. For example, if you compare, the highest value for standard reduction potential is for fluorine. So fluorine F2 to F minus is the highest value, which is around 2.65 volts. Okay. And the lowest value is for lithium. That is lithium plus to lithium. That is minus 3.03 volts. Okay. So if I want to construct the best cell possible, okay, whether it is feasible or not, theoretically, if you want to create the best cell possible, then you make fluorine to get reduced, and lithium to get oxidized. So if I make an anode reaction like this, anode reaction is lithium changing to Li plus 1 electron, while cathode, if at all I make it as, you know, cathode, if at all I make it as F2 plus 2 electrons to give 2F minus. This is the best possible theoretical cell which you can get. That is, the E cell in this case will always be equal to how much of E naught of oxidation plus E naught of reduction that will happen. Or E cell will be equal to E naught of oxidation in this case is how much? 3.03 is the oxidation value. The reduction value is 2.61. So which makes it 5.68 volts. Suppose if at all I write the E naught cell formula only in terms of E naught cell formula only in terms of reduction potential, then I can write it as E naught of reduction at cathode minus E naught of reduction value at anode. This is only reduction values. So reduction value of cathode is 2.65 minus reduction value of anode is minus 3.03, which is same 5.68 volts. So remember, you can write the formula of A naught cell as this way, or you can write the formula of A naught cell as this way. Got it? But this is the standard reduction potential. So this is the first idea you should have about the table, like which one has more reduction potential and when. Next thing we need to know is that uh, the next higher values of the reduction potential that includes will be this. F2 is the most oxidizing. F2 is the most oxidizing here. Clear? After that comes, I'll write down the strength of oxidizing agents. Strength of oxidizing agents. So, strongest oxidizing agent includes F2. Then O3, ozone. Ozone will be very strongly activating. Then S2OA 2 minus. Okay, is a very strong oxidizing agent. Then PbO2. PbO2 is the next one. After that comes MnO4 minus, right? Uh, then comes gold Au3 plus. Then comes chlorine. Then comes Cl2. After that comes Cr2O7 2 minus. Then comes Br2. Then comes Br2. And after that we will get, yeah, here we'll get mercury, or it Hg2 plus, right? And then comes iodine here. After that, we will get silver Ag. Okay. I think silver will be before. Wait, sorry, let me rewrite that. Br2. After that, we will get mercury. We'll get Hg2 plus. Then comes silver Ag plus. And after that, we'll get I2. And then comes copper Cu2 plus. Now, listen up. These are all the oxidizing agents which would have greater value than hydrogen. Okay, H plus. Got it? H plus is 0. H plus is assigned as 0. Above that, if you have to remember, this is the value you need to remember. Okay. Within that, if you notice, right? Within that, if you notice, there is one thing. By metals, if you notice, which are the ones which get better oxidizing agent, that includes gold, Au3 plus, comes Hg2 plus, got it? Then Hg2 plus, then comes silver, then comes copper 2 plus. Okay, these are the four important golds you should remember. Okay, I mean, these are the four important metals you should remember. Got it? Now, anything which is below hydrogen, that means metals having, right, negative reduction potential. Negative reduction potential that includes iron, Fe plus 3 to plus 2 plus Fe plus 3 to Fe. Got it? Like that, if you take Pb2 plus 2, Pb, got it? Sn2 plus 2, Sn, nickel 2 plus 2, nickel, and cobalt 2 plus 2, cobalt, cadmium 2 plus 2, cadmium, zinc 2 plus 2, zinc, manganese, aluminium, magnesium, sodium, calcium, barium, cesium, potassium, and last comes lithium. Okay, this is the order also you need to remember. Okay, manganese till lithium, this is the correct order you need to remember. That manganese will have relatively or more reduction potential compared to aluminium, magnesium, sodium, calcium, barium, cesium, potassium, and lithium. Clear, everybody? So make sure you are aware of this. Okay. right? Knowing this, next thing we got to understand is what is the importance of a salt bridge. Salt bridge, which is connecting the two electrodes, right? Um, right. It is basically in inert electrode, okay, which is connected to both the half cells. And these will have inert electrodes connected connected both sides of anode and cathode must have, you know, must have same ionic mobility of ions present in them, same ionic mobility of cations and anions. Clear? And it should minimize liquid junction potential, and maintain neutrality. Maintain neutrality. So these are important terms which you need to understand when it comes to salt bridge. It will always try to maintain the neutrality on both the solutions. Any kind of junction potential, that means it should not happen that the electrodes, ions from cathode to anode are directly taking a route through salt bridge. So it should stop those ions from coming through the salt bridge. Okay. Next, the examples for salt bridge, if you notice, that includes KCl, okay, KNO3, NH4Cl, and NH4NO3. The mixture of these are also called as agar-agar gel. Agar-agar gel. Okay. This is the basic idea you need to have for salt bridge, guys. Next term we need to understand is Nernst equation. Nernst equation. Delta G is equal to delta G naught plus RT ln Q. This is what we encountered earlier, right? As a thermodynamic equation, isn't it? Here, delta G can be represented as NFE cell, that is not at standard conditions. Delta G naught is at NFE naught cell, this is at standard conditions, minus. If we substitute both of them, then we will get this as E is equal to E naught minus 0.0591 or NF by RT. Okay. So you'll notice that. Sorry, RT by NF. RT by NF into ln Q. If we substitute these values of constant, we will get this as 0.0591 by n log of Q. And this is the Nernst equation which we'll be using. Got it? Now, what is Q? Q is the reaction quotient. Reaction quotient. So basically, if you have a reaction like AAB, BB giving CC plus DD, then Q shall be concentration of C bar C, D bar D, and A bar A, and B bar B. So these are concentration terms, but not exactly concentration. These are relative concentrations. So this does not have any units, remember. Okay. Which means, suppose if you have like this copper 2 plus hydrogen gas is converting into copper solid plus 2H plus aqueous, right? Then instead of representing everything in concentrations, we have to represent everything in activities. The activity of copper 2 plus can be represented in concentration terms. The activity of H2 gas is represented in terms of partial pressure. This has solids and pure liquids will not have any activity, while here we represent this in terms of concentration. So Q would be H plus square by partial pressure of H2 into concentration of Cu2 plus. So it's not like you have to convert this pressure into concentration term or something. Okay. It should be written the way it is. Clear? So this is the value of Q for this. Understood? So Nernst equation mainly represents how to relate the electrode potential at various concentrations here. Got it? So typically, if the half cell is also given for half cells, also, let's say I told you the reduction half cell of hydrogen. Let's say this is how it is being given. Then how do we represent the E H plus to H2? This is the reduction. That should be equal to E naught of H plus to H2 minus 0.0591 by 2 electrons transferred log of pressure of H2 by H plus concentration whole square. That's how you represent. So by this terminology, I'm sure you have understood how do we see the same. Okay. Then, right. Next thing we need to understand is how the thermodynamic relation with Nernst equation. Thermodynamic relation with Nernst equation. See, we know that delta G can be represented as minus NF E cell, and you know that delta G can also be written as delta H minus T delta S. So, if at all I differentiate this delta G with respect to temperature, this is a constant value that will become 0 and this will become delta S. So, from here we could write this delta S is equal to minus delta of dou of delta G by dou T. Hence, delta G can be again rewritten as delta H minus, and this minus minus will become plus into dou of delta G by delta T. Okay. On the other hand, we can also write delta G is equal to minus NF E cell is equal to delta H plus T times of dou of minus NF E cell by dt. So if we write that, we will get delta H. This equation is important. Minus NF E cell, correct? Plus NFT dou E by dou T. Dou E cell by dou T. And this is usually at constant pressure. Got it? This is the equation you should remember. Okay. Next thing. So from here, uh, either you write in terms of dE by dt. So this is delta H representation. If you want to write only in terms of dE by dt also, you can write that. All right. So you can see uh, delta S can also be written as NF dE by dt at constant pressure. Okay. And dE by dt, you notice this is called temperature coefficient. Temperature coefficient. Okay. Right. Please remember these terms. It will be useful for solving. Next, what are the different types of cells you will come across? First one is gas ion half cell. Gas ion half cell. Gas ion half cell means I have H plus converting into H2 gas plus 2 electrons. Let's say if this is how it has been represented. Then E naught of H plus to H2 is sorry E of H plus to H2 is equal to E naught of H plus to H2 minus 0.0591 by N. In this case, it is 2 log of pressure of H2 by H plus concentration whole square. That's how you represent E. Got it? Now, how do we write in terms of half cell notation here? See, because it is a reduction, it should always be written after the salt bridge. So, after the salt bridge, anything which is in an ionic form should be written first by H2 gas by PT solid, because this would only happen on an inert electrode. You have to represent the inert electrode as well. Second one is metal metal ion, metal metal ion half cell. Okay, that is Mn plus n electrons changing to M solid. So E of Mn plus to M is equal to E naught of Mn plus to M minus 0.0591 by N log of 1 by Mn plus. Okay. So this is the reduction part. So you'll put a double line here, then Mn plus by M solid. This is the representation. Third one is very important. Metal insoluble. Metal insoluble salt anion half cell. So if we have to represent this half cell, check out. Suppose if you have AgCl as a insoluble salt and that is getting reduced. So the reaction would be like this. Silver plus Cl minus aqueous. Okay. For that, how do we write? So E of, we write it this way. Cl minus to AgCl to Ag is equal to E naught of Cl minus to AgCl to Ag minus 0.0591 by 1 log of simply Cl minus concentration. Why? Because this is solid, this is solid. So it will be simply Cl minus concentration. Okay. So see, these kind of half cells where concentration is only dependent on the anions here or cations, that is called as reference electrodes. So these kind of electrodes can be used as reference electrodes. Okay. Now we have lots of electrodes to be represented this way. Suppose if you have to represent in a notation, double line here, then remember the ion should be always represented first. Then the salt which is getting reduced to certain part. This is the way to represent. Okay. So keep this in mind. Few examples in this case will be Pb to PbSO4 and SO4 2 minus. Okay. Hg to HgSO4 to SO4 2 minus. Okay. Hg to HgO to OH minus and Hg to Hg2Cl2 to Cl minus. The last one is important. This is called calomel cell, and this is also one very important reference cell. Calomel cell. Okay. So how do we write the calomel cell? See, if you are writing it as a cathode, so we need to show the reduction, which means I would expect that Hg2Cl2 must be accepting 2 electrons. This is solid to convert into 2 Hg solid plus 2 Cl minus aqueous. This must be the case. So how do we represent E now? E of Cl minus to Hg to Cl2 to Hg is equal to E naught of Cl minus to HgCl2 to Hg minus 0.0591 by 2 log of Cl minus whole square. So this is the way you represent the cathode. Since you know how to represent the cathode, you can always do the same thing for anode also. Got it? You can always write the same thing for anode as well. Okay? Correct? See, whenever calomel cell is being taken, calomel cell is being identified as different natures. One is called normal calomel, normal calomel electrode, normal calomel electrode. Correct? Normal means generally we take one normal solution of KCl in this. Okay. If it is given decinormal, which means you are taking 0.1 normal KCl. Got it? So if at all you read it this way, that is what we need to understand. Okay. Next, another example which I took was Hg. Which one did I take it? HgO, right? HgO solid plus 2 electrons plus H2O liquid will convert into Hg plus 2 moles of OH minus aqueous. Again, use this equation, write down the value in this case. Okay, next. Before going further into the next cell, one very important aspect what we need to learn is Latimer, okay, Latimer equations. Suppose if you have something like, a reaction that is happening where you have, let's say, Fe, half reactions which are taking place. Fe plus 3 electrons is giving Fe. For this, the reduction, the electrode potential is given as E naught 1 and Fe plus 2 electrons is getting to be Fe and this is E naught 2. And now using these two, you got to figure out what will happen between Fe plus 3 towards Fe plus 2. Let this be E naught 3. Then how do we relate these three? Okay. To relate these three, you need to first represent them only in terms of energies. See, electrode potentials are intensive properties. Intensive means they are independent of how many moles of electrons it is consuming. Correct? Therefore, we cannot simply add these equations. We can add these equations, but we cannot add their respective electrode potentials. But delta G is an extensive property. So delta G or delta G naught are extensive properties. So they can be added. So now, if you take this as equation 1, equation 2, and equation 3, so it is clear that if at all I make 1 minus 2, I'll be able to get 3. So therefore, 3 equation is 1 minus 2 equation, which implies delta G naught 3 is equal to delta G naught 1 minus delta G naught 2. So delta G naught 3 is minus NF, N3F E naught 3 is equal to minus N1F E naught 1 minus of minus N2F E naught 2. So if I remove this F also and minus also, I'll get E naught 3 into N3 is equal to N1 into E naught 1 minus N2 into E naught 2. So in the above example, if you notice, in the above example, if you notice, it will be E naught 3 is equal to E naught 1. E naught 1 is 3 times of E naught 1 minus, right, 2 times of E naught 2 and divided by 1. This is 1. So therefore, E naught 3 is equal to 3 E naught 1 minus 2 E naught 2. That is how you relate. Okay. In a similar manner, when you have when you have the sparingly soluble salt, okay, how do we relate this? See, another example here. Suppose I have silver plus one electron ions giving silver, and let this be E naught 1, and AgCl plus one electron is giving Ag solid plus Cl minus aqueous, and let this be E naught 2. And then AgCl solid, if it is in equilibrium, to give Ag plus aqueous plus Cl minus aqueous, right? For this one is delta G naught 1, for this one is delta G naught 2, this one is delta G naught 3. This is equation 1, 2, and 3. So let us try to understand how to get 3 out of this 1 and 2. Okay. So if you just simply subtract 2 minus 1, we should be able to get what is, sorry, here it is solid. No, gas, aqueous only, right? So delta G aqueous in this case will be equal to, so 3 can be represented as 2 minus 1. Okay. So delta G naught 3 can be represented as delta G naught 1 minus delta G naught 2. Okay. Now, since this is an equilibrium reaction, so I could write this as minus RT ln KSP, because this equilibrium is because of sparingly soluble salt. We can write this as KSP. Therefore, minus RT ln KSP is equal to delta G naught 1, which is minus N1 F E naught 1 minus of minus N2 F E naught 2. Okay. So if you remove this minus also, I'll get this as RT. Why? And if you notice, the N factor is same in both the cases. So it will be RT by NF ln KSP, that is equal to E naught 1 minus E naught 2. E naught 1 minus E naught 2. Okay. So from here, I can write E naught 2 is equal to E naught 1 E naught 1 1 minute, delta G naught, sorry, I have written it reverse here. This should be 2 minus 1. 2 minus 1. So 2 minus 1. Here also it should be 2 minus 1. So you can notice this delta E naught 2 is equal to E naught 1 plus RT by NF ln KSP. Achha, now what is E naught 2? E naught 2 is this one, right? Cl minus 2 AgCl to Ag, and that is equal to E naught of Ag plus 2 Ag plus RT by NF, you know that 0.0591 by N log of KSP. So this is an extremely important relationship whenever we want to relate. Suppose most of the questions this value is not given, only this value is given. Okay, so first you need to calculate this E naught value to do any solving part. For that, this will be very, very useful. So E naught of silver would be given, KSP value will be given. Use that first, calculate what is E naught for sparingly soluble salt. For every sparingly soluble salt, we can relate with one of its electrode like this, one of its metal electrode. Okay, and that will be useful for solving. I guess this part is clear, guys. So when it comes to metals insoluble salt, this form is very important. Next, fourth one, fourth type, if we notice, fourth one is about oxidation and reduction. Oxidation, reduction, half cell. Here, oxidation and reduction, both of them are happening in same state. That is Fe plus 2, Fe plus 2, right? Uh, sorry, Fe plus 3 plus 1 electron is giving Fe plus 2. How do you represent here? Double line, which means salt bridge. After that, you write it as Fe plus 3, comma, Fe plus 2. Because they are in the same form, that is, they are in the same phase, you don't have to write a line here, okay? So Fe plus 3 to Fe plus 2, and then a line to represent that there is an electrode. So it can be a platinum electrode or any electrode, okay? This is how you will represent it. And E naught, sorry, E of Fe plus 3 to Fe plus 2 will be equal to E naught of Fe plus 3 to Fe plus 2 minus 0.0591 by 1 log of Fe plus 2 concentration by Fe plus 3 concentration. So this is how you represent the half cell. Okay. If the reduction is happening in this way, you will represent it this way. Okay. Another example, which is very standard example, always asked is MnO4 minus in acidic medium. So in acidic medium, this is the reaction you need to remember, that Mn will convert into Mn plus 2 and 4H2O with accepting 8H plus. So in this case, how do you represent the E here? E of MnO4 minus to Mn plus 2 is equal to E naught of MnO4 minus to Mn plus 2 minus 0.0591 by 5 log of Mn2 plus concentration divided by MnO4 concentration multiplied by H plus raised to power of 8. So this is how you represent. Okay. Clear, guys? In fact, the value for E naught of this case is 1.51 volts. Similarly, if it is about dichromate, Cr2O72 minus plus 14H plus 6 electrons, that will give us 2Cr plus 3 plus 7H2. See, these two are sometimes not given in the questions. This is something which you are expected to remember, especially for manganese and dichromate. You are expected to remember. So from there, you would write this as E naught E of Cr2O72 minus to Cr plus 3 is equal to E naught of Cr2O72 minus to Cr plus 3 minus 0.0591 by 6 log of Cr plus 3 raised to power of 2 by Cr2O72 minus concentration into H plus concentration raised to power of 14. Yeah. So this is the value which we will have. Okay. So I think I gave you enough idea about this one. How do we represent it? Now, typically how the questions are framed, let me show you that. Okay. First question type here is, okay. Now it has been said that a cell is given like this: silver AgBr to Br minus, then a salt bridge Cl minus to AgCl to Ag, which is getting reduction. He asked find relation between Cl minus to Br minus, if this is how it is being asked. So first, you got to write the anode here. Anode here is Ag solid plus Br minus aqueous is becoming AgBr plus 1 electron is being released. Cathode wise, it is AgCl plus 1 electron is converting into Ag solid plus Cl minus aqueous. Overall reaction, if you notice, overall reaction, what do we have is AgCl, Ag solid plus AgCl plus Br dot is giving AgBr plus Ag plus Cl minus. So well, these terms are similar ones, right? So these are all in solid state, so we don't have to worry about it. So Q would be simply equal to Cl minus divided by Br minus. Cl minus divided by Br minus. Okay. So now what we will do? We will put back in this equation. So E cell is equal to E naught cell minus 0.0591 by n log of Q. This is what we know, isn't it? Okay. So here, if it is given, find the relation between these two when E cell is 0. Some condition will be given like this in all the questions, these type of questions. Always this condition will be given. Either E cell is 0 or E cell is 1.1, something. Some value would be given. So suppose if E cell is 0 here, correct? Then E naught cell will be equal to 0.0591 by n log of Q. E naught cell. What is E naught cell here? E naught cell is reduction at cathode minus reduction value at anode. So E naught of reduction. What is getting reduced here? Cl minus to AgCl to Ag minus what is getting oxidized here? So Ag to AgBr to Br minus. This is the way to write, sorry. But we have to write only the reduction particle. So that is Br minus to AgBr to Ag. Okay. Like I said, these values are usually not given to you. What is the value given will be only silver values. So you can write this in terms of that silver values. Alright. So how do we write that in terms of silver values here? See, A naught of Cl minus to AgCl to Ag is equal to, just now we have derived it above. I told you this formula is very, very important. Okay. While solving, you will be using this a lot of times. So therefore, this will be equal to E naught of Ag plus to Ag plus 0.0591 by n in this case is 1 log of Ksp of AgCl. Similarly, I can write it for E naught of Br minus to AgBr to Ag, which is equal to E naught of Ag plus to Ag plus 0.0591 by 1 log of Ksp of AgBr. So you could see one with AgCl, the other one will AgBr. Now, this is the difference we are talking about, the difference of these two. So the difference of these two will make it, these two to get these 0. So what do we have? So E naught cell will be equal to, these two will get cancelled because difference of these two we have to take. And here we will have 0.0591 as a common factor and log of Ksp of AgCl by Ksp of AgBr. So if we back substitute that, we will get this as 0.0591 log of Ksp of AgCl by Ksp of AgBr, which is E naught cell, that is equal to 0.0591 by 1 log of Q. Q is what? Q is Cl minus concentration divided by Br minus concentration. Correct? This is Q value. So you can see these two will get cancelled. So simply the ratio here is same as that of their Ksp ratio. So Cl minus divided by Br minus, which was the question asked, is equal to Ksp of AgCl by Ksp of AgBr. That is the final answer. Okay. So I want all of you to go through it once again thoroughly. Please check the question, everybody. It's a very standard question that will be asked. Please check how to do that. So why is E cell is 0? No, that was a condition taken, Ram. Okay. What if the question was given E cell is 0? For it, it might happen that E cell value would be given something in another some other question. Okay. That was just a condition taken. Done? Right. Next. A lot of time you might be asked also to figure out, the graph and the efficiency of galvanic cell. Efficiency of galvanic cell. It is represented by eta, which is how much is the work output divided by how much amount of energy that was input. So the work output is the delta G naught of the cell and input is the delta H of the cell, right? Delta H of the cell. Clear? So which can be written as minus NF E cell mod by delta H of the cell. Clear? Delta H of the cell, we have learned it how to represent that. Delta H of the cell can be represented as uh, NFT into dou E cell by dt, that is with respect to temperature coefficient, and minus NF E cell. This is what we learned. So we can use this formula, try to figure out what is delta H and then calculate eta. This is a very standard question again. You'll always get this question, okay? Remember. So you'll be asked to calculate efficiency. For that, you'll be given temperature coefficient and E cell value. Use that value, you'll be able to get this. Right? Sometimes the same question can be put in terms of the graph also. So that is, if it is E cell versus temperature. Okay. So in that case, this E cell, if you write it in terms of value here, that would be equal to minus delta H cell by NF, right? And plus NF will get cancelled. So T into dE cell by dt. Clear? So this is the slope. This is a positive slope at constant pressure, and that is the intercept, y-intercept value. This is how the graph would look like. Okay. So I guess this value is also clear how to use this. Next, um, you might also be asked Latimer curve questions, Latimer diagram questions. I'll take one example. Latimer diagram, Latimer diagram examples. If you notice, Cl minus is converting into Cl2, it is converting into ClO minus aqueous, and E naught is given here. E naught value is given here as minus 1.36, and E naught 1 here, E naught 2 here is given as minus 0.4 volts. You are asked calculate the E naught 3 value for this one. This is how the Latimer diagrams will be given. Okay. Based on the diagram, you should be able to represent what are the equations. So Cl minus is converting into Cl2 first. Obviously, here it is getting oxidized. So which means half plus one electron. So that's how it is getting oxidized. So E naught 1 value is a oxidation potential, which is 1.36. Next, Cl2 is converting into ClO minus. Cl2 is converting into ClO minus. Okay. So obviously it is again gaining electrons here. So it is a reduction. Uh, it is a reduction value. Sorry. Uh, yeah. So it is again an oxidation value because chlorine is getting oxidized again. So this reaction would be something like this. Some OH minus must have been added, although OH minus is not a part of redox. So that plus one electron plus H2. Then it all makes sense. Why? Because Cl2, if you put this as half here, so here one chlorine at zero oxidation state, here one chlorine is at plus one oxidation state. So which means one electron has been lost. Okay. So this is also an oxidation reaction. This is also an oxidation reaction. And the third one is also oxidation. So Cl minus is directly converting into ClO minus. Okay. So which means if I add these two, it is like OH minus is present here. It will become ClO minus plus electron plus H2. Okay. Plus electron plus H2. Okay. So if I take 2 OH minus, that is what it should. So this is also an oxidation. So our object is to get this equation using these two equations. For E naught 1 value is given, E naught 2 value is given, which is minus 0.4 volts. Okay, clear? So what, like I told you earlier, we cannot add the E naught values, but we can definitely add delta G naught values. So delta G naught value here I can say delta G naught 3 is equal to delta G naught 2 minus, sorry, plus uh, delta G naught 2 plus delta G naught 1. So just add them. So it will be minus N3F E naught 3 is equal to minus N2F E naught 2 minus of minus N1F E naught 1. So that minus will get cancelled. So E naught 3 will be equal to, this is anyway 1 is equal to 1 into E naught 2. E naught 2 is minus 0.4 and minus 1 into E naught 1 minus 1.36, that divided by 2 electrons, because here the lost is 2 electrons, not 1 electron but 2 electrons. So this electron plus this electron. So divided by 2. So you should be able to get the answer. Okay. So this value is coming as minus 0.88 volts. So I guess the questions on Latimer is clear. So this type of questions would be usually asked. Okay. See, in the earlier question, what we did, okay, let me take one more of a similar kind here. Suppose I gave you like this, you know, calculate E naught of half cell, E naught of half cell, which is Ag NH3 twice plus aqueous plus an electron is giving silver plus 2 moles of NH3. What are the values given? Ag NH3 twice plus converting into Ag plus aqueous plus 2 moles of NH3. Okay. This is not mentioned directly. It will be given as K formation. K formation of Ag, sorry, K instability. Inst. This is how it is being written. K inst of Ag NH3 twice plus. This is how it is given. And this value is given as 10 raised to power of minus 40. Got it? So now using that, we need to get this one. Okay. So the other form which will always be given is the silver. This value will always be given. Okay. Silver. For that, the E naught value is given. E naught value of Ag plus 2 Ag is 0.8. Now we need to relate this 1, 2, and 3 equation. Okay. So if I put this as delta G naught 1 and this is delta G naught 2 and delta G naught 3. So we need to represent this delta G naught 1 in terms of delta G naught 2 and delta G naught 3. Right? So which you can clearly see that these two will get cancelled. So it is an addition of these two. So delta G naught 2 is equal to delta G naught 1 is equal to delta G naught 2 plus delta G naught 3. So delta G naught 1 can be written as minus N1 F E naught of that particular electrode. In this case, let me put it as 1 here. Delta G naught 2, it is about the equilibrium here, right? So this is about an equilibrium, right? And this equilibrium will be in this forward direction. The forward direction, we read it as instability. So we read it as minus RT ln K instability and minus plus of minus N2 N3 F E naught 3. Okay. So N1 is 1. So E naught is equal to RT by F ln K instability minus, okay, sorry, plus this entire thing is been gone, minus is gone. So N3 is also 1 into F is gone and into E naught 3. This is E naught 1 and that is E naught 3. So what is E naught 1? E naught 1 is silver NH3 twice plus reducing to silver is equal to RT by NF is 0.0591 by 0.0591 by 1 log of K instability constant plus E naught 3. E naught 3 is what? AG plus 2 AG. So again, you can see no matter whatever you do, the formula will always come to be similar thing. That is E naught of simple cell plus 0.0591 into log of that equilibrium constant. That equilibrium constant could be KSP, it could be instability constant, it could be anything else. But for these kind of questions, every time you relate, as long as you know this idea, it will be very, very easy. Okay, right. Next thing we got to understand here is what are concentration cells. Concentration cells. See, in a concentration cell, we use the terminology. There are two types of concentration cell. One is electrolytic concentration cell. Second one is electrode concentration cells. Electrolytic and electrode concentration cells. What is true for all the all the concentration cells is E naught cell must be 0 for all concentration cells. Right? That is one thing which is always true. For example, if I take it this way, PT solid by H2 gas by H plus aqueous and double line here H plus aqueous line H2 gas line PT solid. Okay. Let this be at partial pressure P1, concentration C1, C2 and P2. In that case, half cell, we can write it as H2 converting into 2H plus 2 electrons. This is anode. Next, we have cathode. Cathode would be 2H plus 2 electrons is giving H2. So if we add both of them, then I'll get Q. Q is equal to uh, pressure of H2, right? Pressure of H2 at cathode into pressure of, concentration of H plus square at anode divided by pressure of H2 at anode into H plus concentration square of cathode. So that is equal to Pressure of cathode is P2 into this one is C1 square by P1 into C2 square. So that's how you relate with the Q. Got it? And since E naught cell is 0, E cell will be equal to simply minus 0.0591 by 2 log of this one. So P2 by P1 into C1 by C2 whole square. Yeah. Now, this entire value, if you notice, this entire value, if it is positive, correct, this E cell will be negative. So, this is a condition we got to understand. So, P2 C1 square, if it is greater than P1 C2 square, then E cell will be less than 0 and this is non-spontaneous. So, the cell remains non-spontaneous. But if P2 C1 square is less than P1 C2 square, then E cell will be greater than 0 and this will remain spontaneous. This will remain spontaneous. Okay. So that's how you decide the concentration cells. All right. Which one is going to be what? Now, suppose if I give you an example like this, example as Ag to AgBr to Br minus, double line here, and Cl minus to AgBr, sorry, AgCl to Ag, right? If this is B naught, this is not a concentration cell. Remember, it's not a concentration cell. Okay, because these two are different electrodes altogether. These are different electrodes. Their E naught values are different. Okay, clear? So here, this is not a concentration cell. So just you need to remember this part. So I suppose this part is clear, everyone. So we'll stop it here.